Okay, whoopsie. In this video, we are going to just look at some basic, get out of there. We're going to look at some basic measurement issues. We're going to have two videos. The first one, we're going to just be dealing with units and significant figures, and the second one, we'll talk about vectors. But here, I just want to do a brief overview. It's in the chapter 1, on units, dimensional analysis, and significant figures. Okay? Just for perspective, there are three basic types of quantities we're going to start with, and those are length, mass, and time. So length right here is just basically our fundamental SI unit is going to be meters, and it just gives you a sense, first of all, of basically in meters what the size of each of these different quantities are. And it's kind of interesting to look at just to get a sense of the various range. And then you'll be seeing these prefixes depending on the size of the quantity. So if you have something that's 10 to the minus ninth, say 10 to the minus ninth meters, that would be a nanometer, and sometimes we just call it a nanometer. Each one of these prefixes goes with the power that is connected to it. So you can get more familiar with those as well as we go through it. Mass, our fundamental unit of mass in the SI system is the kilogram. Kilogram on Earth weighs about 2.2 pounds, to give you some perspective. And these values give you a huge range of different size masses between different things. So you see the Earth is about 100 times more massive than the Moon. The Moon is about 20 orders of magnitudes more massive than a shark, etc. Okay? And the last unit that will be fundamental, length, mass, and time. And our fundamental unit of time is going to be in seconds. And again, each one of these values here is just giving you a sense of scale. Okay? Now, just for a quick review, in chemistry, you went over the structure of matter down probably to the atom, and you basically know that an object consists of individual units, I guess you could call them, that we call atoms, which consist of a nucleus that has things called protons and neutrons in them, and protons have positive charges, neutrons have no charge, and around them in a kind of a cloud of probability are electrons, which are negatively charged particles. But also inside neutrons and protons, you have smaller particles in the standard model of particle physics. We've seen them in particle accelerator reactions, and these are called quarks. These are there's a proton or a neutron. A proton is two up quarks and a down quark. You don't need to know too much about that right now. This is the old school model of the atom, a nucleus with these atoms in orbits. We now know that they're not really orbiting like a planet orbits a sun. It's more of a distribution of probabilities, and we'll talk about that way later in the course. Okay? I think we did that already. So a neutron has an up and two down quarks. A proton has two ups and a down. And I think there's 6 flavors of quarks, if I have that right. Okay, so in SI units, we have different, we can have mass in kilograms. Mass in kilograms, length in meters, and time in seconds. And so these are just different units in SI system. CGS system is metric, but the basis is centimeters and grams rather than kilograms and meters, and you can see the difference. And then in the United States system, we use feet and seconds. Okay? Look at that. Dimensions. Dimensional analysis. So what we're going to do is we're going to see how you can just determine whether something makes sense or not based on analyzing the dimensions. And by dimensions, we mean the dimensions of position are length. The dimensions of time are time. And velocity is a length per time. Acceleration is a length per time, or a length per time squared. So basically, if you look at the units, since velocity is a length per time, and that would be, say, a meter per second. If you take a length per time squared, which is an acceleration, and multiply it by time, you can see that velocity is dimensionally equivalent to an acceleration times a time. So what you see is this is units of meters per second. This is units of meters per second. So an acceleration times a time is in fact a velocity. So velocity is a times t. Now position is a length, but we know that if we just multiply a length times a time over time, you still have a length, and that's a length per time times a time, and we found here that a length per time is that's a velocity. No, yeah, length per time is a velocity. So what we got, what am I doing here? Oh yeah, length per time is a velocity, so we got velocity times a time. Position is a velocity times a time. Velocity can be measured from an acceleration times a time. Units will come out as meters per second. Position, velocity times time, which is a meters per second times a second, is a meter. But we also know velocity equals a times t, so velocity times time has the same units as at squared. And in fact, we'll find out later that specifically the position is with an initial velocity of 0 is equal to 1/2 at squared. So that's how you analyze dimensions. There it is. Okay? Another thing that we have to, if we're going to make measurements, we got to talk about uncertainty in measurements and sig figs. So for example, if I've measured the area of this thing, this rectangle, and I measure 16.3 centimeters, I always have an uncertainty in the last digit I measure. So maybe I have my measuring device. I'm not sure it's 16.4 or 16.2, but it looks like it's closest to about 16.3. To be accurate, I would say my length is 16.3 centimeters plus or minus an uncertainty of 0.1. So this is my best estimate. I think it's 16.3 centimeters, but it could be as low as 16.2 and as high as 16.4. And same with the width. So when I multiply them together, even though I get a value of 73.35 square centimeters, I have to round that to the minimum amount of sig figs I've got, which is 2. There's 2 sig figs here, there's 3 here. When I multiply them together, I can only go to the closest, the smallest value of sig fig. So I'm going to get 73 square centimeters is my best estimate. And then we'll talk about later what my uncertainty in the 3 is. And there are different ways of doing that, which we'll talk about more together than me doing it on the video. Okay? And again, if you're given a value, you can review the rules, but if you have something to the right of a decimal place, you don't count sig figs until you get to the actual numerical value. This is just a placeholder, so this only has 1 sig fig. This has 2. This one we don't know. It's not specified. The best I can say for sure is it's got 2, but if I put in 1.500 times 10 to the third, then I've got 4 sig figs. And if it's only 1.50 times 10 to the third, I've got 3. In this case, I've got 2. So, and again, the rules for dealing with something with how many sig figs they've got, we'll talk about in just a second, actually. Okay, so again, this just shows you how you can write this in a way that if you want to be clear that 300 is 3 sig figs, you can put a little dot there. And we're not going to be, super crazy about this, but it is important when dealing with measured values, understanding the idea of uncertainty in a measurement and what, your measurement really tells you. Okay? When you're adding numbers, you got to go to the last decimal place you've got. So if you add, as I say multiply, I mean add, maybe I said add. 123 plus 5.35 gives you 128.35, but you can only go to the decimal place that's least accurate. So if I add those together, according to the sig figs, the best I can do is say it's 128. And it works the same way in subtraction. You only go to the level that you know. Here, though, I know I'm to 3 decimal places beyond the decimal point, so I can go to the third spot. But I still only have 1 sig fig in the result, even though I've got 4 in 3 in the actual values. But my result only has 1 sig fig. Okay? Now, anytime you do a calculation where things are uncertain, you're going to have an uncertain. In real life, you're going to have an uncertainty. Of course, it's always going to be somewhat uncertain. Now here, it's not quoted exactly what the amount of uncertainty in each individual measurement is, but I can, just based on the values I've got, I can get an estimate of a range in uncertainty, because you can see I'm going to multiply these two and divide it by this. But the order of operation is going to make a difference in the final value. If I multiply the top two, I get this. And then if I divide and I round to 3 sig figs, and then I divide, I'm going to get 8.79. But if I do it in a different order, if I divide this by this first, I get 3.75 when I'm going to the number of sig figs I've got. And then when I multiply it by 2.35, I get 8.81. And then in the third method, I do it in a different order, and I get a different final value. So based on the 3 methods, you can see there's an uncertainty even in just doing the calculations. And I might say this is 8.81 plus or minus 0.03. Now, we'll clarify this a little bit in when we go to do this together. But I just wanted to lay this thing out. There is, in any measurement that's measured values, there's going to be an uncertainty in the measurement. And there's another method to do this where, I could also look at the uncertainty specifically. If I measure the value and get the uncertainty, I can then propagate it through the calculation. We'll do that in a different time. But the main point is any product or division, you can only have in the result of that operation as many as the minimum number of sig figs in any of the individual numbers. And so that's the best I can do. If I do several operations and I've got a range in values, for example, I do them in a different order, it gives me a sense of my uncertainty in my measurement. Okay. Just might realize there's some basic conversions we're going to have to do sometimes. You're going to convert miles to meters to kilometers. These are what the conversion rates are. If one is, for example, to convert 15 inches to centimeters, and I know that there's 2.54 centimeters per inch, basically I'm multiplying by 1. 15 inches times 2.54 centimeters per inch, this value is just the same, they're the same thing, so I'm multiplying by 1 in physical reality. And you can see that the units cancel just like they would algebraically, and I convert 15 inches to 38.1 centimeters. Okay? So that's something you're going to need to do at times. Okay, finally, and this is a very brief introduction to what's called order of magnitude estimates. A lot of times we just want a rough estimate, what's the total mass of, the people on Earth, and you have some people that are 75 kilograms and some people that are 125 kilograms. And you can just take an order of magnitude and estimate and say they're all about 100 kilograms. And then use that basic number to find out something. For example, the total mass of people, you'd multiply, say, 100 kilograms times 7 billion people and get the total mass of people on the Earth. It's not going to be exact. It's going to be within, times 2, times up to maybe times 10. But it gives you an idea of kind of the size of the thing you're looking at in general. And that's something we want to maybe practice with. It's a useful tool. We can do a lot of basic understanding of systems without having to get really specific by being able to do that. Okay, so now I got to turn off this PowerPoint. Let's see. You can ignore me from here on. I got to go back to turn off the screencast. All right, where is it? There it is. No. QuickTime. Okay. What am I doing? File. Screen recording.